Welcome to this session.
Hello, Mandal, are you still there?
No, I think he has somehow got disconnected.
I see. So, let me just ask once more. Mandal, are you around? Okay, if not, let me just take over for this talk. So, the first speaker is Suvankar Chakraborty from INST Mohali. And Suvankar, over to you. So you have 25 minutes and 5 minutes questions.
Yeah. Thank you, Pratapda, and thank you. Let me start with thanking the organizer, not only because of giving me this opportunity to discuss about recent work, but also because of giving us the opportunity to listen to various fantastic work. So is my slide is properly visible to you, or it is kind of splitted into two slides?
No, it is fine. It is fine.
It is fine, but you have the presentation mode that is on your computer. It's fine. We can proceed with this. But it could have been just a single screen, but we can proceed.
How about this?
This is what you want. Yeah, let's start.
Okay. Okay. So my name is Suvankar Chakraborty. I'm working at Institute of Nanoscience and Technology. Today I'm going to talk about some unusual magnetotransport properties like Planar Hall effect, Anomalus Hall effect, Shubnikov-de Haas oscillation, appearance of Berry phase, and possibility of looking into chiral anomaly in potassium tantalate based system. We think that this could be a new kit for a spintronic clock. So this side basically represent the overall idea of our research. We are working on low dimensional electron with high mobility, which is moving under some electric field, and because of this, the momentum and the spin of the electron are locked with each other. So we are working on oxide thin film, superlattice, or interfaces. And this is one of the TEM image of our sample, which shows a very atomically well-defined interface between two oxide materials. So if you think about physics, the two most important pillars of physics are, number one is special theory of relativity and quantum mechanics. When they merge each other, it forms what is known as Dirac equation. This Dirac equation and related physics was mainly exclusive for high energy physics. Until recently, people have observed the appearance of Dirac, Weil, or Majorana fermion as a quasi-particle excitation and related phenomena in condensed matter physics. So this kind of physics reflects non-trivial Berry phase, chiral anomaly, and Rashba spin split band, and so on in condensed matter physics. So we asked the question, can we realize such kind of people? Of course, we will have observed this in other materials, but we asked specifically the question, can we realize this in oxides or not? I will try to give an idea why we want to interested to see this in oxide, so that we can see more than what people have observed so far. So before starting anything, I'd like to acknowledge the people who are constantly supporting us inside INST, my students, collaborators, and IISER Mohali, then IISc Bangalore, Bose Institute, BARC, and internationally also we have few people helping us. And in terms of funding, we have been funded generously by DST Nanomission, DAA BRNS, and INST Mohali. Okay. So today I'm going to talk about the things which have been done by my student Neha, Anshu, Ruchi, Anamika, and Nand Kumar. For the completeness of this talk, let me tell you what is perovskite oxide. So perovskite oxide has a general formula AbO3, where A is an alkaline or rare earth ion and B is in transition metal. So this is a very simple cubic structure where B is occupying the corner of the cube and surrounded by 6 oxygen atoms, and A is sitting at the center of the cube. Why this kind of material is interesting? You think of any physical property starting from superconductivity, magnetism, ferroelectricity, you can see almost all the physical properties in perovskite oxide. Not only that, you can see the correlation between these kind of physical property, which gives rise to what is known as emergent physical properties. So today we are going to talk about, or we're going to focus mainly on two-dimensional electron gas formed at the interface of two insulating oxide. This is not a new story. What new ingredient or masala we want to add in our system are, number one, strong spin orbit coupling and magnetic interaction. So what I'm going to show first, I'll show you the realization of a new interface with two-dimensional electron gas having very strong spin orbit coupling. Number two, I will show that this is the highest spin orbit coupling. Then I will discuss about very unusual magnetotransport properties such as Planar Hall effect, anisotropic magnetoresistance, which could not be explained from so far known the theory of magnetotransport. Then I will give you an idea why we are confused between if the system has Rashba effect or it's a wire-like material. So this is we are now trying to understand now. Then I will try to give you an idea of the dimensionality of this conductance channel. If time permits, then I will talk about the observation of non-trivial Berry phase and signature of Rashba split band in one of the oxide interfaces. In conclusion, instead of giving a complete concluding thing, I will try to end up with several open questions. So those who are interested may have a look at these our recent publication, and what I'm going to talk about are covered in all these papers. So for the students and the completeness of this talk, let me start from give you an idea of what Rashba effect is. Let's start from a free electron model where you have the Hamiltonian p square by 2m and energy has a dispersion relation k square h square k square by 2m, where you have a single parabola in EK space, and if you think you have a single Fermi circle. Now, if you think this electron is moving with a relativistic velocity, under the application of some electric field, which could be internal or external, then in the rest frame of this electron, this electric field is now converted into a magnetic field, and the spin of this electron is now quantized based on the direction of the motion of this electron. And so the spin and the momentum of the electron is now locked to each other. What happens physically is that instead of having one energy band, this energy band is now split into two energy bands, and you have, instead of one Fermi surface, you have two Fermi surfaces, where if you look into the K space, the spins are rotating in one direction in one Fermi surface, and in another it is rotating exactly opposite direction. So it has a two different type of spin chirality. So what are the ingredients you need for this? You need strong spin orbit coupling, some kind of electric field, and a relativistic electron. So why this kind of mechanism or this Rashba is important? It has an application. If you think of application, this is one of the milestone for key to realize what is known as spin transistor. In terms of fundamental science, if you look at this band crossing point, near the band crossing point, you have a linear dispersion. So it's like a Dirac cone, and you have the idea of spin chirality that could lead to the idea of Berry phase and magnetic monopole and so on and so forth. So it has an aspect of topological aspect as well. So the idea of this high dimensional electron gas at the interface of two insulating oxide is not new. In 2004, people had shown that if you make an interface of lanthanum aluminate and strontium titanate, both are insulating, but the interface become highly conducting. And it is the resistivity versus temperature data, where the resistance decreases with decreasing temperature, showing that this metallic nature of this material. And it shows in the course of time many fascinating properties. Now we want to know, instead of having STO, strontium titanate, can we think of a material where you have a strong spin orbit coupling? So for us, the obvious choice was potassium tantalate, where it has a strong spin orbit coupling, which is around 400 milli-electron volt. And from old literature, it is well known that if you dope potassium tantalate, it can give rise to very highly mobile electronic system, which can goes up to around 10,000. So this has become an obvious choice for us. So just give me an idea why this kind of interface of two oxide insulator becomes conducting. So there are many mechanism has been proposed, but one of the well accepted mechanism is what is known as polar catastrophe. So if you think of a perovskite oxide, and if you look into each layers, then you can think that each layer contains either BO2 or AO atoms. If you think of strontium titanate, then this BO2 layer has charge neutral layer, and your AO layer, which is strontium oxide layer, also charge neutral. But if you think about lanthanum aluminate, then this BO2 layer, which has aluminum oxide, has a -1 charge, and lanthanum oxide layer, which is a AO layer, has a +1 charge. So you have now +1 -1 charge. This is known as a polar type perovskite oxide, but overall it is charge neutral. Now one can easily show that if you make an interface of a polar and non-polar material, then you have at the interface a charge discontinuity, which gives rise to an electric field which looks like a step-like function, and the corresponding potential is now diverging. Now, to get rid of this diverging potential, one may send half of the electron from the top of this thin film to the interface, and your electric field now looks like a zigzag-like electric field, and the corresponding potential is no more divergent, it becomes a convergent potential. So what are the check of this kind of polar catastrophe scenario? Number one, you need some thickness of this thin film, a critical thickness is needed for the thin film. Number two, half of the electron per unit cell should be doped at the interface. So we are using what is known as pulse laser deposition system to prepare our sample. This is a picture of our pulsar deposition system, and our system is kind of equipped with what is known as reflection high energy electron diffraction system. It's a very unique system, and you look at the diffraction pattern of the electron, and by counting the oscillation in the diffraction pattern when you start depositing, you can exactly figure out how many number of monolayer of the thin film have you grown on the top of your substrate. I'm going to try to cover two materials. Number one, lanthanum vanadate thin film crystal on the top of potassium tantalate along 001 oriented direction, and if time permits, europium oxide thin film on the top of potassium tantalate. So first I'm going to talk about lanthanum vanadate potassium tantalate interface. So we have grown different number of lanthanum vanadate on potassium tantalate substrate 001 oriented, and this is a read intensity oscillation which suggests we are growing monolayer by monolayer in a monolayer fashion, and at different number of thickness has been grown. Then this is the X-ray diffraction pattern which suggests a beautiful quality thin film has been produced, and you can see the Lauwet fringes which suggests that you have a very atomically well-defined interface of lanthanum vanadate and potassium tantalate. So this is the resistivity data of different monolayer of sample. ml correspond to monolayer. If you see, this is the temperature versus resistance. For 2 monolayer sample, it's completely resistive, but after 3 monolayer, the resistivity becomes decreases with decreasing temperature, and it becomes independent of number of monolayer of the thin film you are growing. So this is the conventional Hall measurement, which suggests that the charge carrier density has around 2 into 10 to the power 14 per square centimeter charge carrier in the system, which is actually equal to half of the electron dope per unit cell. So let me give you an comparison of known system, and you can realize that this is a really and perfect example of polar catastrophe. If you think about lanthanum aluminate and strontium titanate system, then it has a critical thickness, but it has a charge carrier density less than half electron dope. If you think of gadolinium titanate strontium titanate interface, it doesn't need any critical thickness, but it has a half electron dope. But in our case, lanthanum vanadate and potassium tantalate, both criteria has been satisfied that it needs a critical thickness and it has a half electron dope system. And so this is the number of monolayer grown, and this is the mobility versus charge carrier density, number of monomer of the lanthanum vanadium thin film grown. Then we had performed the normal magnetotransport measurement where you send the current along X direction, apply the magnetic field along Z direction, and you measure the voltage along the X direction. And you could see the appearance of weak antilocalization, which is a signature of strong spin orbit coupling. And fitting this equation, we could figure out the amount of spin orbit coupling is around 4.4 Tesla, which is largest among all perovskite oxide. So I'm going to give you some analogy that motivated us for further measurement. What is that? If you think of a wire material, then what you have two Dirac cones separated in K space with two different spin chirality. When you apply a magnetic field, then a charge pump from one direction to another direction, that gives rise to negative magnetoresistance, and it also at the same time prevent the backscattering since they are well separated from each other. And when you change the angle between the current direction and magnetic field, the magnetoresistance amount changes as similarly. Now, if you think of Rashba, I don't want to say they are exactly same, but the similarity is that here also you have two types of spin chirality, but instead of having two Dirac cone, it is circulated by one Dirac cone. So the signature of Weil fermions are, or Weil type signature in transfer properties are negative in-plane magnetoresistance, planar Hall effect, and anisotropic magnetoresistance. So we asked the question, can we see this kind of things in our material or not? So this is the transport geometry. You apply the current along X direction, and magnetic field making an angle theta with the Z direction. So we define our XY plane as the interface of this material or the two deck of the material. And you can see when theta equal to 0, that is magnetic field is along the Z direction, it gives a positive magnetoresistance. But when theta equal to 90, that is B parallel to the current, you see a negative magnetoresistance. And this negative magnetoresistance becomes positive magnetoresistance with increasing temperature. This is very similar to what people have seen in topological materials. So now let me give you a comparison of our sample with known topological material. Please note now the definition of theta has been changed from here to here. So now theta equal to 0 is I parallel B. So you can see for our material, I parallel B has a negative magnetoresistance and I perpendicular B, but is out of plane, has a positive magnetoresistance. This is the out of plane measurement. And in a well-known Weil material, the situation is very similar, that when you apply the field in direction of current, you have negative magnetoresistance, and perpendicular to that out of plane is positive magnetoresistance. But in case of in-plane geometry, so this is the in-plane measurement. So we are applying now the field in the plane containing the two deck, that is XY plane, making an angle phi with the current. So phi equal to 0, and now in this case theta is of course 0 always. So phi equal to 0 for our material, you see negative magnetoresistance. Even for phi equal to 90, you see negative magnetoresistance, which has a sharp contrast to what people have seen in Weil material. If you change the angle phi in case of Weil material, in plane also you should see a negative to positive magnetoresistance transformation. So now we want to see this what is known as planar Hall effect and anisotropic magnetoresistance. So this is our magnetic transport measurement device geometry, where this is the two deck which is defining the XY plane. You send the current along X direction and you rotate the magnetic field in the plane, and the direction and this direction between magnetic field and the current is defined by angle phi. So what is the measurement geometry? And you measure, either you can measure this perpendicular voltage, which is we call the planar Hall voltage, or you can measure along the direction of current, which we define as anisotropic magnetoresistance. So this is the data rho xy or rho yx, that is the in planar Hall geometry. What are you doing? What we are doing is that you keep the magnetic field constant and you change the direction between current and applied magnetic field, and this is the change in resistance, Hall resistance. And you can see that in any field up to 14 Tesla, it has a twofold type signature, which is kind of fitted by cos phi sin phi dependence. And this is the contour plot of this in phi and magnetic field space, and z direction is the resistance. And you can see that twofold twofold oscillation continues even up to 14 Tesla field. But when we look into the longitudinal resistance, that is the anisotropic magnetic resistance, you can see at low magnetic field, you have a twofold oscillation which can be fitted by cos square phi type dependence. But at high magnetic field, additional peak appears and it can be fitted only by cos square phi, cos square 2 phi dependence. And this is the corresponding contour plot. And you can see that around 8 or 9 Tesla, starting from 2-fold symmetry, it goes to a 4-fold symmetry. So I would like to give a very kind of simplified picture to understand this. What is the scheme for that? Let us think, what is the total Hamiltonian? Let's take the total Hamiltonian. The first part is the H0, is the free electron Hamiltonian, and this is the Rashba part. And so this is the total Hamiltonian. This H0 contains both free part and the Rashba part, and V is the perturbation coming because of the magnetic field we have applied in the plane. And we have assumed that this V is as a perturbation in the system. Now you can think that there are two reference frames in the system. One is the rest frame of this, one is the laboratory frame which is at rest, and another is this magnetic field frame of reference which is rotating. So one can basically define this conductivity matrix or this equation in the frame of reference of the.
Right, Suvankar, you've completed 20 minutes, so
yes,
maybe in 5 minutes you can complete the talk.
Sure.
Questions. Right.
Sure. Okay, so you can calculate this resistivity in the frame of reference of this rotating frame. And so what you basically calculate, the this transition matrix probability, or what is known as by using the Fermi-Goldel rule. And you can calculate the resistance which is perpendicular to the applied magnetic field is basically gives you nothing but the Drude resistance. So the important component is the R parallel to the B. So we could calculate this, and we make a transformation back to the laboratory frame, and we can see that the resistance, longitudinal resistance, has a dependence of cos square phi, which we have already seen, and your planar Hall has a cos phi sin phi dependence, which we have already seen. So we could basically understand that at least at the low field, this thing can be explained by using a Rashba type physics. But now we are confused because let's think about this geometry that you apply the magnetic field along the direction of this current. So if you apply the magnetic field along the direction of the current and wants to measure the transverse magnetic field in a 2D material, you should not see any Hall because your V cross B term is 0. And if you think from our Rashba picture, this was the expression for Rxy, which contains cos phi sin phi term. So when phi is 0, you should not see any Hall effect. But this is the data of our Hall data when you measure I parallel B configuration of the applied magnetic field, which has a B linear plus B cubic dependence. And it was been kind of reported long back for a wild fermion system in a 3D like material. One could expect to see B linear plus B cubic system. So these give us a hint that we might have looking into some wild type physics in our system. And what happens? Why this you should see negative magnetic resistance? Negative magnetic resistance means when you apply magnetic field, your resistance decreases. That is, your relaxation time increases. So in case of wild physics, people says that this corresponds to what is known as axial relaxation time, which is different from the normal 2D relaxation time. And when you apply I parallel B, this TA becomes larger than tau 0. That is, your axial relaxation time should be longer than your Drude relaxation time. And we have fitted this with our system, and we could see a 50 time enhancement of this axial relaxation time. And this is the temperature dependence of tau A by tau 0, and this vanishes at around 70 Kelvin. And our planar Hall effect also vanishes around 70 Kelvin, which suggests that this planar Hall effect and this kind of appearance of axial relaxation time or the axial current has some intercorrelation with each other. So our model could not explain the appearance of negative magnetoresistance, then unusual angular dependence, which is different from wild type behavior, and doubling of periodicity of this anisotropic magnetoresistance. So I have completed this part, and I don't think I have time. I would like to take 2-3 minutes to just give you an idea of this europium oxide KTO interface. Europium oxide is an insulator. Potassium tantalate is also an insulator. But when we prepare the interface of that, it becomes highly conducting. That also shows the appearance of Anomalus Hall effect. In addition to that, we could able to see the quantum oscillation in resistivity as a function of applied magnetic field, which is known as Shubnikov-de Haas oscillation, and it shows 2 types of oscillation, which we could figure out that correspond to one 3D and 2D channel. So the important point, when we plot this in the as a Landau-Fan diagram, we could see appearance of it doesn't go to 0, and we could see the appearance of non-trivial Berry phase in the system. And also we could see the strong appearance of weak antilocalization and strong spin orbit coupling as well. So this gives us the idea that we have 3 bands in the system: one trivial type parabolic band, one non-trivial band with Berry phase, and which has a 3D type nature, and another 2D type band which is also non-trivial in nature. Then by using completely transport property, we could figure out the possible band structure of the system. I don't have time to go into the detail of that. So we end up with this following open questions. Number 1, what is the band structure of this system? Because we still don't know the band structure of this system, neither experimentally nor theoretically. Then what is the explanation of negative magnetoresistance in the system? Then explanation of planar magnetoresistance and planar Hall effect at high magnetic field. And what kind of topology this system has. It's a non-trivial or trivial. And at least a pictorial understanding of how the chirality evolves with temperature and how the band topology changes with magnetic field. So what we have shown the realization of a new interface with very strong spin orbit coupling, and this is highest among any oxide perovskite material. Then we show extremely unusual magnetotransport, which can be partially explained by Weil and partially explained by Rashba physics. And also I could not show, but we had shown that this system is not really a 2-dimensional system, but it has a charge carrier distribution along Z direction. So it's a kind of quasi 3-dimensional system. So I end up on this talk by giving you by asking the question, what we are looking at, is it a Rashba, is it a Weil, or is it something else? And thank you very much. And if you are interested, you can see some recent publication which is based on KTO material, and here they are listed. Thank you very much.
Thanks, Suvankar, for finishing it well on time. The talk is open for questions. If you have questions, please ask questions one by one.
Yeah, Mandal, can I ask a question?
Sure, go ahead, please. Yeah.
Thank you, Suvankar, for a beautiful talk. Very nice work. But I have a basic question. I think the your argument about wild nature could be questioned a little more carefully, because in wild, whatever you call this Adler-Chiral anomaly is strictly valid for longitudinal magnetoresistance. And when you showed the plot, when you see the negative magnetoresistance 5 degree, 25 degree, one has to be a little careful whether they really there is any topological aspect to it. I mean, and I just want to know, because potassium tantalum oxide, the spin orbit coupling is coupling from K2 only, right?
Right.
So all this MR, what is the role of interface between LVO and KTO? Rather than focusing on the wild part, which I didn't find direct evidence for. Yes.
Sure. I completely agree with this. That is why I want to emphasize. See, although from the out of plane part, it looks like it has a positive to negative magnetism transformation. If go to 525, it goes away. But in case of in plane magnetoresistance, it never vanishes. It's always negative magnetism, which is a complete contrast to it while, and the idea of while, because if you make a little deviation of phi, even if the in plane, it should go from negative to positive. So really it is questionable we are seeing while or not. I completely agree with that. But at the same time, what bothers us or not bothers us is this. So this cannot be explained from any known physics, because when you apply magnetic field along the direction of current, there is no reason that you should see the transverse resistance, because until and unless in your equation of motion you have a Berry curvature term. So there must be some kind of Berry curvature coming from something which giving rise to this P cross sigma type term, right? So this is why we are kind of at least thinking about while. I'm not saying at all it is while, but what my point is, there is some kind of Berry curvature, and to know this, we must know the band structure of this material.
Thank you. Thank you.
Yeah, Shouvik, maybe you can ask a quick question.
Thanks, Mandal. Yeah, great talk. I just had a quick question about, so you showed that the LVO KTO is behaving like an ideal polar catastrophe material. I was wondering, do you have any idea why one would expect a priori for this material to be perfectly showing polar catastrophe where the others are not? And the second is that about the, similar to the previous question, is there any—
Shouvik, maybe one question. Sorry,
Okay.
we are out of time. So Suvankar, can you please ask that one question? Maybe later on you can go to a chat room. And
so we can discuss it over telephone also. Just quickly, I'm telling you one thing, and instead of saying why it is showing polar catastrophe, I'm telling you what was the problem in LAO-STO. Once you put this aluminum, it always has a tendency of making the thing oxygen vacant. And LAO has a much stronger growth condition, reducing growth condition, which makes this strontium titanate oxygen vacant. Although you might have a polar catastrophe scenario there, but it could be dominant. You have a mixture of oxygen vacancy and polar catastrophe. And in case of gadolinium titanate, what happens? That it has both. This is a Mott insulator. What happens? The band structure is oriented in such a way you don't need a polar catastrophe. It already went into the band structure of STO, and there is an electron hopping from one conduction band to the other's valence band. Sorry, one's valence bands to other conduction band. So there is a paper by Tanushree Shah Dasgupta in scientific report that explains these things very well.
Thanks, Suvankar, for your nice talk. I think we have to move on. Please discuss in one of the rooms. Okay, thank you very much. Over to Shouvik. Shouvik, I'll give you a reminder at 20 minutes time that you have 5 minutes to wind up so that we can have questions. So the next talk is being given by Shouvik Chatterjee. He's going to talk about controlling magnetoresistance in semimetals. Over to you.
Is my screen visible?
Yes.
Okay. All right. Thank you, Mandal. It's really a great pleasure to share some of our work in this conference. So I'd be primarily talking about magnetoresistance in semi-metallic systems. And as you all know, that magnetoresistance has been studied for quite a few decades. But what is different here, I would like to highlight, is that we are trying to take a one step forward and trying to see if we can really control magnetoresistance in semi-metallic systems by using techniques of epitaxial synthesis, and which we think would actually allow some of these material properties to be utilized in functional devices. But at the same time, we think that these can also have the potential to throw additional insights in some of the underlying physical properties. And I'd try to show two different examples. One is that of lutetium antimony, the rare earth mononuclide, which shows a large non-saturating magnetoresistance. And if time permits, I'll also talk about topological states in a half Heusler compound, platinum, gold, lutetium antimony, which shows a very strong linear magnetoresistance, and how we can control it and show that emergence of a quantum Hall-like phase. Okay. So before starting, I just want to highlight that we are a very new group. and we work on quantum materials. We just completed 1 year, and we work on various different aspects of quantum materials as is listed here. If you're interested in what we are doing very recently, please stop by at the poster of Dr. Shivesh Yadav, who would be talking about our efforts in stabilizing manganese 2 platinum palladium thin films in a half-Heisler structure. Okay. All right. So just to give a brief background, we are mainly interested in intermetallic systems, primarily half-Heuslers and full Heusler and their different variants, particularly because they are multifunctional intermetallic systems, much like a counterpart, if you may, of the perovskites, as you heard earlier in the talk. And you can realize many different exotic phases of matter, including unconventional superconductivity, magnetism, topological phases, and all. But it offers you a very large design space. And here I'm just trying to highlight the crystal structure. As you can see, you can create a half-Heusler by combining. You can think of it as a combination of a zinc blend, which is like in regular 3-5 semiconductor has a zinc blend structure and an FCC. And if you want to go to the full Heusler, you can think of it as a zinc blend plus 2 FCC sublattices. Now, if you take out all the tetrahedral interstitial sites, what you end up getting is a rare earth mononuclide, which has a rock salt structure. So today I'll be talking about one example, which is the rock salt lutetium antimony, and another, if time permits, of a half-Heusler platinum lutetium antimony structure. So just to give a brief background, this lutetium, the rare earth mononuclides in general have been of interest for quite some time, particularly because there are a lot of actually technological applications. They can be utilized to create terahertz polarizers and emitters, lots of applications in thermoelectrics and so on and so forth. But one of the other advantage also is that you can stabilize these material systems on 3-5 semiconductors. You can see I'm plotting the lattice parameters of many different compounds, and they have quite a good lattice match for many different 3-5 semiconductors. So one can actually utilize this particular aspect to create biaxial strain to control their electronic properties. And also you can create these kind of quantum dots or one-dimensional nanowires, which you can grow in a self-assembled manner. And here, what I'm showing you here is an RBM antimonide quantum dot, which is embedded in a 3-5 gallium antimonide matrix. But today, in this talk, I will focus mainly on the electronic structure aspect, which is okay. I seem to have a
Sorry, what's the problem, Shouvik?
I seem to have a chat window open. I can't get rid of it. Wait 1 minute.
Just click on the chat window again, and it should close.
Okay, I think I can just maybe get oh, sorry.
Yeah, that's okay. There must be a close, or just ignore it for now.
Yeah, it's fine. Okay, sorry about that. So yeah, as I was mentioning, this talk, I would primarily talk about the electronic structure and also the large magnetoresistance, and whether we can apply the tools of thin film synthesis in trying to control some of the electronic properties. Particularly, I will talk about the effect of dimensionality, and also whether there is a role of interface in such heterostructures. Okay, so just to give a brief background, I mean, as you all probably know, that in general, if we talk about a semi-classical treatment, what you generally expect is that your magnetoresistance which follow B square behavior in low fields, and then it saturates. And if you look at typical metallic systems, these are of the order of 2 to 3%. But recently what was realized is that there are a class of intermetallic systems where this magnetoresistance can be very high, of the order of 10 to the power 6. This one way this can come from is electron hole compensation, where if you have a perfectly electron hole compensated material system, then your magnetic resistance actually does not saturate and goes up at B square. But what was also quite interesting in these sorts of material systems is that they also show a similar magnetic field and temperature phase diagram, as I'm showing you here for 4 different material systems. And many of them, tungsten ditelluride, for example, were shown to have a non-trivial topology. So there were ideas whether the non-trivial topological aspects, whether they're playing a role in this material, in these kind of observation of large magnetoresistance. And one does expect to have this sort of a band inversion in these class of materials in rare earth mononictide, where basically you expect a band inversion between the rare earth D and pnictogen P, as is shown in here, and you would expect that you will have this non-trivial surface states residing in this projected gap. So we went ahead and tried to see if we can create these materials in epitaxial thin film form. And we use this technique called molecular beam epitaxy to the first order approximation. You can think of it as an atomic spray painting, as I've shown here. So what you have are very well calibrated effusion cells or furnaces, if you will, from where you can which emits a very particular amount of molecular beams. We can calibrate them very well, and then they gets deposited on a preheated substrate, and you can create your desired materials with atomic precision. So here what I'm showing are the electron diffraction images, which we can take in situ while growing these materials. And what you see here is that when we start growing lutetium antimony, you get a very sharp 1x1 reconstruction, as you would expect for a rare earth mononictide film. We can also look at the transmission electron microscope. Here, what I'm showing you is one such lamella from the heterostructure that we grew on lutetium antimony on gallium antimonide. And I think you can very clearly see a sharp transition from a zinc blende type structure to a rock salt structure. We can also then, once we have our film, we can look at the electronic structure. And here I'm showing you Shubnikov-de Haas oscillations from where we can extract the different frequencies just by doing a fast Fourier transform. And from there, by using this Onsager relation, we can get an idea about the different wave vectors of the Fermi surfaces in this material system. This is just to orient what you would expect for lutetium antimony, for example. This is from density functional theory calculations. What you see here at the center, we have 2 hole-like pockets. And at the zone edges, you have an elliptical electron-like pocket. And when we analyze our data from the Shubnikov-de Haas oscillations, what you see exactly, we see, we get both the components from the electron-like pocket and the hole-like pocket. And when we calculate the carrier densities, we find that at least in the bulk limit, there is a very good compensation in the sense that you have almost equal numbers of electron and hole-like carriers. And we can also get an idea about the anisotropy ratio, which is basically a ratio between the semi-major and the semi-minor axis of the ellipse, which is about 3, which again matches very well with our DFT. So no surprises here still, at least till this point. So, but what we can do, we can also get an idea about the electronic structure very directly by utilizing this technique of angle resolved photoemission spectroscopy. For those of you who might not be very familiar, this is basically a spin on Einstein's photoelectric effect. So what we are doing here is that we are coming in with an incident photon light and kicking out a photoelectron. And now if you can measure this photoelectron, its kinetic energy and angle at which it is coming out vis-a-vis some particular crystallographic direction of your crystal surface, then by utilizing the standard energy and momentum conservation principles, you can back calculate the quantum numbers of interest, which are the in-plane momenta and the binding energy of the electron when they were in solid. And because this is an electron spectroscopy technique, you might readily realize that this is quite surface sensitive. So one needs to preserve the pristine sample surface of your thin film that you have grown. So we developed this vacuum suitcase, which then allows you to transfer the material from one system to another without exposing it to ambient air. And you can see it here attached to a ARPIS system. So when we do this right, we can actually get a direct visualization of the electronic structure. And what I'm showing you here basically in this panel B is the cut through the three-dimensional Brillouin zone through this gamma point, which is at the center. And you can directly see there is a very nice correspondence around the gamma point. You have these two hole-like Fermi surfaces, and at the zone edge you have an electron-like Fermi surface. So you can also take various cuts. That is, if you take a cut along this direction, which is shown in here, actually it's this one, or you can take a cut along this direction, which is the gamma X direction, and you can get an idea about the band dispersions. And what you see here that they match very well from your density functional theory calculations. And same goes on for the electron pocket. You can take a cut here and get an idea about the wave vectors for both the semi-major and the semi-minor axis of the ellipse. So what we find is that it agrees very well with the DFT, and also there is no indication of any surface state, so it is topologically trivial. So what we can conclude here that yes, in this material system, the magnetoresistance is primarily driven by the electron hole compensation. Now, this is what you would be able to do in also using a bulk single crystals, although there is some difficulty in cleaving this material because it's a three-dimensional system, but still you can do what I have shown this for. But we wanted to take a next step forward and ask that if your understanding is really correct, that can we now really control this electron hole compensation and try to see if we can tune the magnetoresistance. And we will utilize here the technique of dimensional confinement. What we will try to do is we will try to thin down our thin film because it is a design choice, so we can create materials of arbitrary thicknesses. And when we do that, what we find is that there is a very dramatic reduction in the magnetoresistance, and in very thin limit, it actually starts to saturate. Now, another aspect that I want to draw your attention to is in the Hall resistance. So what you see here that it changes when you go from thick to thinner films, it changes from electron-like to hole-like behavior. Furthermore, I think this is more clear. When I go from the 40 monolayer to 20 monolayer, it goes from the nonlinear to a linear Hall-like behavior. So basically what you are seeing is that you have at a thicker film, you have a multi-carrier behavior from the Hall, which goes to a single carrier dominated behavior as you thin down your material system. So the natural question is, okay, so can we understand this transport behavior? So we again take help of our ability to directly visualize the electronic structure in this material systems, and we can do it for also very thin films. And what I'm showing you here is the same cuts as I'd shown earlier for different film thicknesses. As you can see here that your Fermi wave vector actually is going down as you go from the 40 to the 6 monolayer limit, but the electron-like pocket actually does not suffer that much of a change. We can do it a little more quantitatively, as I'm showing you here. So this is our data, and you can see that yes, the hole-like pockets, this beta and the delta actually goes down, but the electron-like pocket actually does not change that much as we grow thinner. So we try to understand that by doing slab calculations where you can mimic the electronic structure of ultra-thin films. But we find that actually this does not really match our experimental data. You can see that the alpha semi-minor actually also reduces as you go down in thicknesses. That is one. The second part is And the second also, we can also try to do the same thing by looking at the quantum oscillations, and we do get quantum oscillations till 20 monolayer. And you can see here that the frequency corresponding to the electron-like pocket actually suffers very little change, but where there is a very strong change in the hole-like pockets. So this again actually corroborates what we see in the ARPAs, that as you go thinner, we can actually lift the electron hole compensation, where we have a much higher carrier concentration for the electron-like carriers as opposed to hole-like carriers. But now there are two issues here. So one, as I just mentioned before, that our slab calculations really cannot capture the correct trend, though we saw that in the bulk limit, DFT does a very good job of representing the actual electronic structure that we measure. That is one. And the second, if you remember a couple of slides back, I showed you that in the ultra thin limit, you had the Hall behavior actually changing from the electron dominated to being hole dominated, which is clearly not the case what we are seeing from our ARPAs and the quantum oscillation measurement. So can we reconcile what we are seeing in our measurements? So now for that, I want to remind you that, when we grow our thin films, it is not freestanding, but we also have a substrate. So thereby we also have an interface. So what we try to do is just analyze our data by utilizing a 3-component Drude model, where you have a component from the electron-like carriers, another from a hole-like carriers, and also some interfacial carriers. And when we analyze it, we can clearly see that we have quite a large concentration of the interfacial charge, which is of the order of 4.38 10 to the power 14 centimeters squared. That roughly translates to about 0.8 holes per 2D unit cell. And the 2D unit cell, we define it like this here, this violet dotted line, which has actually 1 lutetium, 1 antimony atom per unit cell. And furthermore, you can see, just looking at the trend as a function of thickness, actually the mobility or actually scales with the film thickness in the thinner limit. That again tells you that here you are dominated by the interfacial scattering, which limits your mobility or the mean free path. And that again tells you that in the thinner films, you are in a quasi 2D limit. Okay. So now we went back to doing the DFT calculations, but this time we explicitly took into account the interface here. And now we do see actually there are the interfacial states which coming from the gallium s orbitals. And if you look at the charge density distribution, you find that although they are very well distributed in plane, they're very tightly confined in the out of plane direction. So we can also get some quantitative numbers by looking at the Fermi surface corresponding to this interfacial states. And what when we calculate the Luttinger volume, it comes out to be about 0.7 holes per 2D unit cell per interface. I want to highlight here, though, that these slab calculations were done using the GGA potential, which is not exactly accurate. What we had previously done for the bulk was at HSE, but then it becomes too expensive. So the number here, you should take it as a lower bound for what we expect in this material system. So now, we also see there's another thing that is happening at the interface. That is, there is also a charge transfer across the interface, and which we can calculate to be about 0.45 electrons per 2D unit cell per interface going to the lutetium antimony side, and also to the gallium antimonite side, though it's very small, which is about 0.05 electrons. And this you can see when we plot this layer resolved density of states. What we're plotting is this density of states when you're deep inside the bulk. There is not much contribution from the
Shouvik, you should wind up in about 5 minutes.
Okay, sure. But when you come closer to the interface, you have a very large contribution from your interfacial states. So now we can also get a handle on the number of electrons that we expect by doing a simple exercise in electron counting. And here, let's assume that in the completely ionic picture at the interface, you would expect that the gallium transfers 1.5 electrons to each of the neighboring antimony atoms. Now, at this particular interface, as I told you, that we expect that 0.45 electrons are transferred to the lutetium layer, and 0.05 are transferred to the gallium antimony layer. So you're remaining at the number of electrons you have at the interface is about 1. So now if it occupies an interfacial band, you expect a 1 hole per 2D unit cell. All right. And of course, this is an upper bound because gallium antimonide has a significant covalent character. So from this exercise, what we can put is a lower and upper bound, which is between 0.7 and 1. And what we find from experiment is that we have about 0.8 holes per 2D unit cell. Okay, so this matches quite well, but let's take it one step further. Now, if we really understand what is happening in our system, we can back calculate that if we have 0.8 holes per 2D unit cell, what we expect is that there are 1.2 electrons at the interface. There is 0.05 that goes to the gallium antimonide. So actual number of electrons which is transferred to the lutetium antimony is about 0.25. Now we can add this 0.25 electrons to our original bulk slab calculations and again recalculate how we expect the Fermi wave vector of the electron pocket to change as a function of layer thickness. And now we really find a very good correspondence with the experiment and the theory. So this was without electron transfer, and this is 0.25 electron transfer, and you can see that we have quite a good correspondence. Now we can take it one step further to give further support that what we are claiming here is actually true. In the experiment, what we find is that, in a natural, in an ideal rock salt structure, if you calculate this angle between the lutetium, antimony, and lutetium, it will be 90 degrees. But at the interface, because there is a bonding mismatch, there is actually a distortion of the lutetium atoms, and which gives you 90. It's a little distorted, so it's about 93 degrees. So what that translates is that if you were to able to calculate the interatomic distance along this column, the first interatomic distance between the lutetium atom will be a little smaller than the rest of them. And this we can actually directly calculate from the TEM measurements on our thin films, and this is experimental data. And what we do here is that we go along these columns, and just for statistics, we do an average over all these different columns going from here to here. And this is what is plotting here. And what then we can calculate this lutetium interatomic distance with 1, 2, 3, 4. 1 is at the first lutetium atomic distance near the interface. Here is the interface here. And what we find is indeed there is a slight, the first lutetium interatomic distance is shorter than the rest of them. So I think with this, and this is just another way of, this is just a little more detail. I won't go into this in interest of time. So what we think is that now in the previous talk, you had heard that this idea of polar catastrophe, where you slap together a polar and a non-polar material, and then you have this polar catastrophe induced 2-deg at the interface. Of course, we know about that we can induce a 2-deg by electrostatic band bending, and this has been very successful in realization of integer and fractional quantum Hall effect, which I'm showing here. But we think is that we have now found another way of stabilizing a 2-deg at the interface, which is more by the chemical means due to the bonding mismatch. Okay, so I think I'm almost, I don't have much time, but I just wanted to show that in this, in platinum lutetium antimony system, we can actually, just by changing the doping in this material, we can go from a very strongly linear magnetoresistance behavior to a phase which looks like a quantum Hall phase. And we can actually establish that this is coming from this. If you look at the conductance plot, this is actually very similar. And we could establish that this is all coming because of the tunability that we can have in the surface and the bulk coupling that changes the behavior from the this kind of a linear magnetoresistance to this quantum Hall-like phase. With that, I'll just conclude. I think there is a very strong opportunity in epitaxial synthesis of the semimetallic systems, where we can really tune their material properties and thereby gain additional insights into the underlying microscopic mechanisms that are at play. So with that, thank you for your attention.
Yeah, thanks, Shouvik. The talk is open for questions. If you have questions, please raise your hands and go ahead and unmute yourself and ask.
Yeah, Shouvik, this is Samuel here.
Yeah.
Actually, you mentioned that depending on the monolayer, there is the electron hole compensation changes.
Yes.
So do you see saturation in your magnetoresistance, because your magnetoresistance was still not saturating?
Yeah. We do see the very ultra thin limit. let me just. And I must also say that there is also influence of mobility here. So you can see that in a very ultra thin limit, it starts to saturate in 8 and 6 monolayer.
Oh, I see. Okay.
So your curve, it curves out. Yeah. Yeah.
Okay.
And there is also this the magnetoresistance. I didn't go into that detail, but the mobility also plays a role in as you would expect in the final value that you get.
Okay, thank you.
Any more questions? Okay. I had one question, quick question, Shouvik.
Yeah.
In your the Planar Hall data that you said, what is the Fermi wavelength here? I just and what is your confinement length? What is the thickness rather?
Sorry.
What's the thickness of the film?
Yeah,
and what is the Fermi wavelength?
So it's 15 nanometers. That is the thickness of our film. And I didn't get into the detail. I mean, let's see, I'll maybe share it. So I can tell about the Fermi velocity, which is about 4.85 10 to the power 5. So the Fermi wave vector is around 0.033. Thanks.
Okay. Okay, we'll talk more about it later. Okay, thank you very much, Shouvik, for a nice talk. We're ready for the next. So the next speaker, if they're here, the next speaker is Santiago Grigera. The title of the talk is Topological Metamagnetism, Thermodynamics and Dynamics of the Transition in Spin Ice Materials under Uniaxial Compression. So over to you. I'll alert you at 20-minute time, and then you have 5 minutes to finish your talk so that we have 5 minutes for questions. So over to you.
Perfect. Thank you very much. Let me start by thanking the organizer for the invitation. It's very nice to be here. It was worth coming, despite it's a bit early here. So I need to confess I haven't been at the earlier talks. I plan to stay later, but not telling this. Okay, so essentially, what I want to tell you about today, it's about this topological transition that happens in this class of frustrated magnetic materials. And I'm going to tell you a bit about the thermodynamics and also something we've been trying to do by putting a little bit of uniaxial compression and seeing how that affects the system. I mean, it's quite that one of the things when you have a frustrated material, one of the things you would like to do to try to mess a bit with that frustration. And here, the way to do it was, of course, to put a uniaxial tension that would start changing the different parameters, the different J's that are frustrated. So let me start by acknowledging my co-worker. So this was done in collaboration with my group here in La Plata, in Argentina, with Rodolfo Borsi, Lucas Pillian, and Pamela Gurciaga. And part of this work was uniaxial pressure was done in Dresden, in Germany, in the group of Andy McKenzie, with Alex Stepke, Mark Barber, Fabian Jersenberg, and Cliff Hicks. And the theory part we'll be discussing with Broderick Messner also in Dresden. Okay, so let me start with a few words about frustration. I mean, all of us who are experimental physicists know a lot about frustration, but the question is, what is frustration in the context of magnetism? And essentially, the simplest definition one can give of frustration is that frustration happens when you have a Hamiltonian that contains interactions whose contributions to energy are impossible to minimize simultaneously. So the origin of frustration, I mean, it is said that the first one to recognize the importance of frustration, as with so many other things, was Anderson. And the myth goes, and I'm not sure this is absolutely true, but the myth goes that Anderson said, wrote in an Aspen conference, he wrote in the Blackboard, frustration is the name of the game. So if you look at the literature for the origins of frustration, the first paper you find is this paper by Toulouse, where he's discussing about spin glasses. And he says, okay, so, and by the way, he has one of the references, so footnote, saying that he's borrowing this word frustration from Anderson. So this seems to be compatible with this story that it was Anderson, the first one who recognized frustration as something important. So Toulouse makes two important questions. The first one is, what is studying disorder systems? How does one distinguish between serious disorder and non-serious disorder? And the second question is there any way which one can give a measure of this? So, okay, so he starts, I'm following his discussion here. He starts with the simplest system. So just a system with pairwise interactions, Ising type spins with pairwise interactions. And he says, okay, let's say I have a square lattice, and here, this is the configuration for my bonds. They're all ferromagnetic. And of course, this is a completely ordered system. Now I take one of the sides and I flip that. And in the sense that I put now all the J's, I flip the sign of all the J's around that side. So I'm adding disorder, but he says this is certainly not serious disorder because it's quite easy to fix it, in the sense that, so if I'm putting blue circles here are spin ups and red circles are spin downs, so I just flip one of these spins and that cures the problem I have. So this is disorder, but it's certainly not serious disorder. And he says serious disorder stems from frustration. And this is now a case where I have a problem. So now I have three J with one sign and one J with opposite sign. So now when I try to put spin up that has a problem with this bond, and if I try to put spin down here, I have a problem with the other bond. So this is a case where I cannot cure the disorder, and where I end up in competing states that give me the same equally bad, let's say, or equally good, depending how positive you want to be about it, configuration. Right, so he goes a bit further, and I'm not going to go into that discussion, but I just say it's very interesting discussion. So he goes about trying to measure this, and he finds a way of measuring it, which is equivalent of trying to define some sort of curvature in spin space, which is, as I say, it's a very nice paper that I recommend. So, of course, there are different ways in which you can induce disorder into a system. Induce frustration into the system. Disorder is one of them. So here, this is the example before I showed you before. One other possibility is to add further neighbor interactions. So let's say if I now add next nearest neighbor interactions to this square, and those I add, let's say they're all anti-ferromagnetic. If I add these two, now I have a problem. If I want to accommodate my spins to fix one of these bonds, I have the problems with the next nearest neighbors. And if I do the other one around, I have problems with these two. And of course, the another way of doing it is simply by geometry. If instead of having square, have a triangle, this is the example one usually finds when discussing frustration. If I have a triangle, I have the same problem. There's no spin configuration I can choose that would satisfy. So now if I look at this from the point of view of an experimentalist rather than a theorist, there are slight differences between these ways of getting frustration. So disorder is something which is, of course, is possible. sometimes it's impossible not to get disorder, but it's not so easy to control. From a theoretical point of view, also, it's not so easy to control disorder. I mean, it's not ideal. Then there's this idea of further neighbor interactions, and this really requires fine tuning. So here you need for your system to have the same next nearest interaction that nearest neighbor interaction. And this is, as you would easily realize, it's very difficult to get experimentally. So if you want to work on a clean system and you want to work with frustration, the obvious choice from an experimentalist point of view is to work with geometrical frustration. And you get all sorts of geometrical frustration. So you can get two-dimensional lattices or three-dimensional lattices. So here I'm putting a couple of examples. You have the Kagome lattice, a triangular lattice. We have a pyrochlore, the CGO. So essentially, this is like stacking different Kagome and triangulars. This would be like stacking a Kagome, alternating Kagome and triangulars give you the pyrochlore or the CGO. So the nice thing about geometrically frustrated systems is, as I said, that they are a clean system, but because they're frustrated, they avoid trivial solutions. So they leave room for more sophisticated and more exotic type of ground states. And in these systems, you can find solids, liquids, gases, quantum liquids, Bose condensation, equivalent of Bose condensation, etc. So the case I want to tell you about today is based on this tetrahedra. And it's the simplest case of the tetrahedra. So we have Ising time spins, and they can point either in or out from this tetrahedron. And the question is, okay, so if I have now a simple nearest neighbor Hamiltonian, what's the ground state of such a tetrahedron? And of course, it's easier just to look at pairs. So now you have, let's say, the possibilities that you have one of these pointing out and one pointing in, or that they're both pointing in or both pointing out. So now, if we look at the projections, you see that if you have a ferromagnetic interaction, the ferromagnetic interaction would favor these two states, right? Because here the projections are essentially ferromagnetically aligned, while if you have an anti-ferromagnetic interaction, you would tend to choose this sort of state where they're all pointing in or all pointing out. Another way of looking at or seeing this is if you realize, you do a bit of geometry, you see that in a tetrahedron, the angle between these center pointing spins is 109.5. The cosine of this angle is exactly -1/3. So essentially your Hamiltonian, in terms now of pseudo spins, of scalar spins, becomes -j/3, the sum of those spins. So here you see that essentially you're reversing the sign of whatever you put in there when you're looking now at the pseudo spins. So essentially the ground state for the ferromagnetic case would be like the ground state for the anti-ferromagnetic scalar case. And again, here you see that this type of Hamiltonian would tend to choose to have one plus and one minus, right? So one in and one out. So if you want, the paradoxical thing is that the frustrated case is ferromagnetic, the case with ferromagnetic interactions rather than the case with antiferromagnetic interactions. So now if you wonder what's the ground state if you have a pyrochlore lattice. So okay, we said we have 6 combinations per tetrahedron. Now you start putting these tetrahedra together, you're connecting them by the corners. So essentially what you have, your entropy of the ground state will be this. You have 2 spins per tetrahedra, so it's 1/2. And now you have 6 choices, right? So these are the 6 possible choices of putting 2 spins out and 2 spins in. But now you have 1/4 chances of matching, right? So when I try to match 2 tetrahedra, I have 1/4 chances of matching those. And that gives us the entropy, which is Pauline's entropy, so K 1/2 log of 3/2. And that's why people started calling the thing spin ice. So now that you realize that this is analogous to ice, there's a lot of literature you can pinch if you want. And here, this argument comes from Onsager. He says, okay, if I want to calculate which are the possible ground state of this system, this is equivalent of piercing. If I have one string and I want to pierce this string through all the sides, that would give me the number of ways in which I can pierce a string through all the sides would be equivalent to the number of configurations I have. I mean, this doesn't seem very useful, but as you'll see quite soon, it gives you a lot of insight into the system. So the type of materials I'll be using in this talk are dysprosium titanate and holmium titanate. We grew these using a mirror furnace. These are very easy to grow, by the way. It's something a summer student can learn to do and get very good quality crystals. These are big crystals. And for some of the experiments, we used an isotopic dysprosium just to have no nuclear moment contribution, right? So to have the cleanest possible system. Okay, so these just to justify the name spin ice, you can do the same kind of measurements that was done on water ice. If you want to check what's the ground state of these systems, you measure the specific heat, you integrate it, and you see that if you assume that you're starting from zero entropy, once you integrate it, you see that you're missing quite a lot, right? So you should be at very high temperatures, you should reach R log 2, and you see that you reach something which is quite below that, and the difference between those two is very close to Pauli's entropy. So essentially, these are nice spin ice systems. Sorry, I didn't say this. So the moments here are big moments. They're 10 Born magnetons, and they're fixed to Ising type excitations with a energy scale of 300K, and the ferromagnetic interactions is of the order of 1 to 2K. So we'll be working around those temperatures. So for all intents and purposes, these are really nice Ising type spins. Okay, so if you now go back to this Onsager spin yarn, if you think, okay, so I have a very disordered system, has this huge entropy, but how disordered is it? I mean, is this a gas type system? And of course, immediately the answer is no, because as I said, there's this correlation coming from the fact that all these states correspond to having this single thread going through them. So if you now calculate which are the correlations in this state, you find that they are dipolar correlations. So the spin-spin correlations are equivalent to dipolar correlations. So one easy way of checking whether this is true in your experimental system is, of course, you look at how these dipolar correlations will look in reciprocal space. You measure, you do neutron scattering, and you compare your measurements with what you expect to find. I would say that these measurements are not beautiful, but at least they hint that this is not a bad explanation, or it's not a bad description of the type of excitations you're seeing. Okay, so how much of a surprise was to find the polar correlations in this system? I would say not a lot, because if you think about the rules that created this system, these rules were saying that the sum, so you have two spins pointing in, two pointing out, so essentially the sum of spins over each tetrahedron gives you 0. And this, if you go to the continuum limit, is equivalent to saying that you have a divergence that is equal to 0. You can go a bit, so that immediately justifies having the polar correlations because you have like an emergent gauge structure. But okay, you can also go a little bit further. This is work by Castelnuovo, Messner, and Sondi. And what you can say is that, okay, now if I start looking at excitations out of this ground state, what I find is that this is equivalent to creating charge in this system, right? So once I start flipping spins and the sum over each tetrahedron is not equal to 0, I can think that that's equivalent to creating a monopolar, a pair, if you want, of monopoles. And you have monopoles of different signs. And of course, you have, depending on how many spins you flip on a single tetrahedron, you have charges of 2 or 4 sides, 2 or 4. And if you look at how these charges interact, they interact like a magnetic Coulomb law. I don't want to go into this, it's a lot of detail on this because I want to focus on the topological transition. Just let me say that how good description this is. Well, if you now think, okay, my excitations are like charges, I can take the bifocal theory for charges, electrical charges translated into magnetic charges, and I can calculate the specific heat. This is this line here. The blue line is using the bifocal. The red line will be using a beta lattice calculation. And when you compare that with what we measure in our experiments, it's a very good match. So essentially, this idea of thinking of these systems in terms of these dipolar type or correlations, it is a very good one. So okay, now I come to what I want to tell you today. It was just a long introduction in case I'm assuming that not many people are familiar with this field. So what we want to do here is to take the spin yarn, this on-target spin yarn, and now we want to apply a field and order these lines and see what sort of transitions you get once you order these lines. So the idea, this is something that was first discussed theoretically by Shouvik and collaborators, including Brother Messner here. This is that now you put a field along 100. I mean, any of the principal directions would work, but you take 100. And now what you do is essentially you lift this degeneracy, you create a single ground state, and now you wonder, what kind of excitations do I have if I'm working at the limit, at the low temperature limit? Essentially, suppose it's impossible to flip any spins. What would the excitations be to flip? So to have single spin flips, right? So what would the excitations be? So let's take then this lattice. Let me just flatten this. I mean, it's not easy to show these things in 3 dimensions. So let me flatten this. I'm looking at the spins projected into one plane. Now these squares will be the equivalent of the tetrahedra. Now you see when I put a field along 100, what I'm doing is I'm polarizing all spins, but by polarizing, I'm not opposing the rule. So I still have 2 spins pointing out and 2 spins pointing in on each tetrahedron. So this field is preserving the ground state rule. So I said, I'm assuming that I'm working at low enough temperatures that the KT is much smaller than J, so these excitations don't exist. So even if those excitations don't exist, I can still take spins and flip a whole line. So this is an excitation that pierces the sample all the way through. And if I do that, you see that by flipping this whole line of spins, I'm still preserving the rule, because still on each tetrahedron, I have 2 spins pointing in and 2 spins pointing out. So essentially, by flipping this, I'm preserving the rule, but I'm creating an excitation. And once I have that, I can move it freely inside the sample. So this is how these kind of excitations would look in 3 dimensions. So one way in which I like to think about these excitations is in terms of superconductivity, if you want. So these are like vortices in a superconductor. So in a superconductor had a zero magnetization.
Right. You've completed 20 minutes, so you have maybe 5 more minutes for the talk, and then some more 5 minutes for questions. So
yes. I'll try to finish in those 5 minutes. So this is like superconductors in this sense. So I have a zero magnetization state, and now the vortices there will be positive magnetization. Here I have a fully magnetized state, and my vortices are, if you want, negative field. Right, so if I do a bit of statistical mechanics on these strings, you see that I have every time I flip spin, that costs me Zeeman energy, but because every time I move one step here, I have 2 choices. Essentially, what I have is that once I put the string, I'm losing from the Zeeman part, but I'm gaining from the entropic part. So if I now compensate these two, I find that I have a critical field, which is KT log 2 over 2 square root of 3. And this 2 over square root of 3 is coming from the projection of spins along the 100 direction. So now my phase diagram looks something like this. I have field and temperature. I have no lines at higher fields and low temperatures, and I have these excitations otherwise. But you see that the thing here is that there's no J into this transition. So no matter how strong my exchange interaction is, I have no J. So what are the observables of the transition? So if I look now at the magnetization, as I said, these are lines of negative field. So once I have the lines, I start depleting. So I start lowering the magnetization. So this is how the magnetization would look at fixed H. And you see that this is like a metamagnetic transition. I have a jump of the magnetization, but it's very special in the sense, or special, let's say, in the sense that it's this topological transition that has no excitations at high temperatures, excitations, sorry, at high fields, excitations at low fields. So it looks like a second order transition from one side. I have a divergence of the susceptibility. I have absolutely nothing from the other side. So people at one point wanted to call this 1.5 type transition because there was something halfway between first order and second order. So if I now allow for some additional excitations, if my temperature is not low enough that I don't have any type of single spin flips, essentially what happens is that this gets a bit softened, but they still preserve the shape. Okay, so let me come now to the experiments. So what we did was to cut samples. These are very small samples because we want to also to strain them. We put them inside a coil that we wound manually around the sample, and we measured susceptibility, and we also measured magnetization using a squid. So this is how the experiments look. This is the magnetization, and this is the susceptibility. This is for dysprosium titanate, and you see that you get essentially some something that looks like because the temperature is not that low, and the reason why the temperature is not very low is because the system, in addition to all the interactions, has dipolar interactions. You see that these are big moments. So it freezes at very low temperatures. So you need to be working in this regime where you have the temperature is low enough that you have this type of ground state, but it's not low enough that you don't have single spin flips. Okay, and this is how the susceptibility looks. And you see again that you have something which is very anisotropic in the sense that the low temperature phase looks very different from the high temperature, sorry, from the high field phase. And this is the same measurement taking now in holmium titanate. And the reason why we did both holmium and dysprosium is because they have the same moment, but they have completely different J. So in the case of dysprosium, J is of 1K, and for holmium is twice that value. Okay, so again, you see here, because J now is a little bit higher, these are also stronger. The comparison with this is the symmetry calculation of what you would expect for that type of transition from this topological transition. You see that the experiments look pretty similar to what you would find. So I come to the phase diagram. This is how they look, and you see I put together here what you get from different techniques like measuring different samples and also measuring AC susceptibility and DC susceptibility and squids. And you see that in both cases you get a single line with error. And as I said, for the case of holmium, the J was twice what you would expect. So in principle, if this were a normal metamagnetic transition, we expect the critical field to be twice as big in the case of holmium than in the case of dysprosium. Let me use the last 2 minutes by telling you what you would expect to happen once you put uniaxial pressure. Essentially, what you're doing when you're putting uniaxial pressure is you're changing these two interactions compared with the rest. And essentially, what you will be doing is you're going from cubic to tetragonal, and you will induce a a polarization even at zero field. And if you look at in detail the theory of this, you'll find that this is a very unusual transition, that it's an infinite order transition. So what we did was to use this type of experimental setup, where essentially what you're doing is putting your sample between these two piezoelectrics, and essentially use three piezoelectrics so that when they compensate each other, and when you change the temperature, the system doesn't add any or remove any tensions. And this is what happens when you start putting uniaxial tension into the system, which, as you see here, it's very little. So we went to -0.1 to -0.8%. Higher than that, the samples break. And now you see that, okay, so if you want to compare this with here we cannot do any DC measurements. So essentially what you do is you measure at different frequencies, you extrapolate that to 0, and now you compare that, you create a phase diagram for the different tensions, and essentially you see that there's almost no difference between them. And when you compare, you put those with the cases where we were measuring in the absence of any uniaxial pressure, we find absolutely no difference. So although the theoretical idea that you can induce this exotic transition applying uniaxial tensions is very interesting, it's well, for the time being, it's well beyond the limit of what we can do without breaking our samples. So the only thing that is interesting one thing that is interesting from putting this uniaxial pressure is that what we see, this is now the imaginary part of the susceptibility as a function of temperature. We see that as you start putting uniaxial tension, there's a big shift in the peak of the imaginary part, which is essentially telling you that the dynamics of the system is changing. This is a quantum effect. This has to do with the fact that you're changing the holmium environment, and now you're making the system, if you want, a little bit more quantum mechanical, and that's why you start seeing a different dynamic. So our plan is to explore these dynamics as a function of uniaxial tension. I won't show you this. This was just a confirmation using neutron experiments. I mean, if you want to confirm that there are lines inside, that the excitations look like lines, you can do a neutron experiment adding the magnetic field. And here what we did was to put a tilted field so that you have a biased random walk, and then you compare the correlations of a biased random walk with the correlations you measure with neutron experiment, and you see that again. This description of the excitations of the systems in terms of strings is a good excitation. It's a good description. So just to summarize, sorry if I went a little bit too long. The idea was to show you that these are interesting systems where different type of physics happen. And I gave you one example where you're looking at one type of topological transition, which was described before in the context of dimers in two-dimensional systems. These are these Castellan type transitions. Okay, thank you very much for
Thank you very much for your talk. I think we have time for one quick question, if anybody has. Yeah, Pratap, go ahead, please.
Hi, Santiago. That was an interesting talk. So, tell me one thing. When you showed that the specific heat, you don't recover the full entropy. Is that because the ground state has a large degeneracy and therefore the entropy at zero temperature is finite?
Exactly.
That is okay.
Exactly. So essentially, if you assume that you're starting from 0, which would be the less biased assumption, then you integrate out and you see that you're missing something. So you say, okay, my assumption was wrong. What I'm missing here should be down there. So this has been a matter of controversy because the system, as I said, the system starts to freeze at around 0.6. So what is that specific heat you're measuring down there? It's not clear. And if you look in some detail, in principle, the system should eventually order, because there are some residual interactions that should order any real system. So this is matter of controversy, but it's as usual. What it's telling you is that the zeroth order description in terms of these fields and lines is a good one.
But when you are saying it freezes, does that mean it orders or it freezes as
no, it freezes completely disordered.
Okay.
So as a matter of fact,
ice.
we've done these experiments where we cool the sample for a whole month. So very slowly for a whole month, and did neutral experiments before and after, and we see absolutely no difference. So essentially, these are extremely long timescales, but really, really long time.
Okay, thank you very much for your talk. I think we are out of time. Let's move to the next talk. Thank you.
Sorry for extending a bit too long.
That's fine. Can the next speaker please come over and sorry. The next speaker is Aastha Vasdev, and the title of the talk is Mixed Type 1 and Type 2 Superconductivity in Palladium Telluride. Over to you. So I'll remind you to finish that you have 3 minutes around a 10-minute time, and then there'll be some time for 2 minutes for questions at the end. So over to you.
Okay, thank you. So today I'll be talking about mixed type 1 and type 2 superconductivity in PDTE2. The superconductivity in PDTE2 has been reported for a long time, but it did not receive much attention because of its low critical temperature. However, after the discovery of Dirac semimetallic phase in PDTE2, the superconducting phase also gained renewed attention because the coexistence of Dirac semimetallic phase and superconductivity in the same material might lead to the topological superconductivity in the system. So here are the experimental evidences of type 2 Dirac semimetallic phase in PDTE2. However, despite the speculations on the possibility of type 2 Dirac semimetallic phase or unconventional superconductivity in PDTE2, the STM as well as heat capacity measurements showed that the superconducting phase in PDTE2 is rather conventional in nature. And however, this superconducting phase in PDTE2 remained conventional was found to be conventional in nature. Its magnetic properties, as far as its magnetic properties are concerned, this superconducting phase remained indeed interesting, because what was observed is that this group initially showed type 1 superconductivity in PDTE2 by the magnetization as well as transport measurements, and later they showed the same type 1 superconductivity by μSR experiment. However, this type 1 superconducting phase type in PDTE2 in a binary compound came to be as a surprise, because these binary compounds are generally expected to show type 2 superconductivity. So later, this type 2 superconducting phase was also observed by Clark et al., where they observed a vortex core at an applied magnetic field of 7 millitesla. So based on this observation, they claimed that the superconducting phase in PDTE2 is of type 2 nature. So after the discovery of this either type 2 or type 1 superconducting phase in PDTE2, we did STM experiments on PDTE2, and what we found is that we actually found the mixed type 1 and type 2 superconductivity in PDTE2, where what we have observed is that the surface of the PDTE2 hosts both type 1 regions as well as type 2 regions coexisting on the surface of PDTE2. I'm not able to move my, So what we observed is mixed type 1 and type 2 superconductivity existing on the surface of PDTE2. So what we observed is that in certain, and these scanning tunneling spectroscopy that we got, we found we look at the magnetic magnetic field evolution, because at different locations. So what we observed is that for certain spectra at certain locations, this superconducting energy gap was found to evolve smoothly with the magnetic field, or the spectra was found to evolve smoothly with the magnetic field, which indicated type 2 behavior, while for other regions where the type 1 superconductivity was reported, was found, the spectra was seen to show the first order disappearance in the superconducting energy gap. So this part revealed type 1 superconductivity, while the smooth evolution represented type 2 superconducting behavior. So the distinction of type 1 and type 2 superconducting behavior by these spectroscopic measurements was already reported in the past by Naidoo et al. In 1996, where they have probed 2 different regions in the presence of magnetic field. What they observed is that in one region, this double minimal structure was abruptly decreased with magnetic field, and the corresponding the variation of superconducting energy gap with magnetic field was seen to be like this, while in certain other regions the spectra, the point contact spectra, evolved smoothly towards the normal state with increase in magnetic field, and in such a case the superconducting energy gap varies smoothly with the magnetic field. So what we observed is that there is an inhomogeneous distribution of critical field on the surface of PDTE2. How in certain cases the critical field was found to be as low as 220 Gauss, and we observed the critical field up to 4 Tesla. The interesting thing is that in the regions where the superconducting critical field, the critical field was less than 300 Gauss, showed type 1 superconductivity, while the higher supercritical field regions showed type 2 superconductivity. And this behavior, so if we look at exactly what happens what is different in these 2 regions, is the kappa, which is less than 1/√2 for type 1 superconductors, and which is greater than 1/√2 for type 2 superconductors. So this difference in kappa was attributed to the inhomogeneity in the mean free path observed on the surface of PDTE2. So this inhomogeneous mean free path would lead to the inhomogeneous critical coherence length, and this inhomogeneous coherence length will ultimately lead to a variation of critical field depending on the type 1 regime, or we are looking at the type 2 region. So this situation is completely different. The Ginzburg-Landau theory fails if the kappa is exactly equal to 1/√2. So this point will be discussed in more detail by one of my fellow students who will be presenting a poster on this when kappa is exactly equal to 1/√2, and here are the details of his poster, so you can go and have a look at it. So just after the publication of our paper on mixed type 1 and type 2 superconductivity on the surface, another Chinese group reproduced our results, and they also concluded that the inhomogeneity in the mean free path is responsible for the type 1 and type 2 regimes. So after this, so as I have already told you, that the inhomogeneity is in the mean free path is responsible for the inhomogeneity in the critical field, the different critical fields observed on the surface of PDTE2. So what we can actually do, we can artificially disorder the system to look at what happens to this inhomogeneity in the mean free path, and what is expected is that, so we did such experiments by intercalating copper between the PDTE2 layers, and what we have observed is that the system becomes homogeneously type 2, and this mixed phase disappears. Reported for mixed for PDT2 disappears, and the system becomes homogeneously type 2, and we actually investigated that phase. So this is the STM image that we got for copper intercalated PDT2. Here the intercalation is copper is 4% intercalated. So these are the defects that were already reported in PDT2. So upon intercalation, what was new, what we observed is new are these dark spots surrounded by this well-defined interference pattern. And we did the spectroscopy at different locations, means near the copper intercalates and away from the copper intercalates. So what we mainly observed are these two kinds of spectra. We mainly got these two kinds of spectra. For one of the spectra, the superconducting energy gap was found to be higher, which is 0.53 millielectron volt, while for the other case, it was 0.44 millielectron volt. But in this case also, the superconducting energy gap is anyway higher than what is observed for PDT2, which is 0.32 millielectron volt. So we can say that effect of this intercalation is everywhere. So when we look at the temperature dependence of this spectra with lower gap, what we observed is that the spectra evolves smoothly with temperature, and finally the spectral features disappear at a critical temperature of 1.62 Kelvin, which is the critical temperature of PDT2. And if we look at the delta versus T dependence, this delta superconducting energy gap is seen to follow the BCS-like temperature dependence. And if we calculate delta by kBTC for the smaller gap, means where the effect of intercalation is lower, delta by kBTC is calculated to be 3.15. However, in the other regions where the superconducting energy gap was found to be, for this spectra where the superconducting energy gap was higher, the critical temperature is seen to be enhanced, while in previous case it was the same as that of PDT2, while in this case the critical temperature is found to be enhanced to 2.4 Kelvin, but the delta in this case also is seen to follow the BCS-like temperature dependence. Now the calculation of delta by kBTC in this case is...
Hi, Aastha, you have 3 minutes to complete your talk.
Okay. So if we calculate the delta by kBTC for this, it is found to be 2.56, while in previous case it was where the effect of intercalation is lower, it was 3.15. So we can say that the higher the effect of intercalation, lower is the value of delta by kBTC, which tells us the electron phonon coupling strength. So means electron phonon coupling strength decreases with copper intercalation. Now, in previous reports on copper, on the bulk measurements on copper PDT2 have reported that this enhanced transition temperature observed in copper PDT2 is due to the enhanced electron phonon coupling strength, as well as the higher value of density of states at the Fermi energy. While in our case, we can rule out the possibility of the enhanced electron phonon coupling strength by looking at the value of delta by kBTC, which decreases with copper intercalation. Hence, we can say that in our case, the enhanced TC is observed because of the increased density of states at the Fermi energy. So we also did magnetic field dependence on various spectra that we observed at different locations on the surface of PDT2. Although the critical field was found to be different in every case, means it was indeed higher than PDT2, but it was different at different positions. The one thing that was common is the observation of type 2 superconducting behavior, the homogeneous type 2 superconducting behavior upon copper intercalation, which was expected because what happens if we introduce disorder in the system, upon intercalation or upon introduction of disorder, the mean free path decreases, and hence the consequent decrease in the coherence length is observed. And this increase in the coherence length leads to an increased kappa, which is increased in such a way that the system becomes homogeneously type 2, means we can say that disorder have pushed the system from type 1 to type 2. So here I would like to conclude my talk that initially we observed on bare PDT2, we observed mixed type 1 and type 2 superconductivity. Upon the introduction of disorder or upon intercalation of copper, the surface becomes uniformly type 2. We did not observe any signature of type 1 superconducting phase in the crystal. In addition to this homogeneous type 2, the critical temperature also gets enhanced, and the effective critical field was also observed to be higher rather than the pure PDT2.
Okay, great. Thank you very much, Aastha. Now the talk is open for questions. Yeah, Pratap, please go ahead and ask questions. So there will be only one question. Yeah.
Aastha,
Yes, sir.
show your fitting,
Sorry?
when you show the feet of your spectra, can you go back to the feet of your spectra? No, not here. Yeah, no, next slide.
Okay.
Yeah, so you see the feet of your spectra actually, though you are showing in a very crowded graph, it's actually very poor. At close to zero field, there is a large deviation, and close to the coherence peak also, the deviation is quite large. First of all, why is this deviation? And secondly, with such deviation, what is the reliability of the parameters that you are extracting?
So actually, if we look at this spectra, although that was crowded, in this spectra, at t is equals to 0, we did not observe any deviation of the fit from the experimental data.
Well, here you are seeing a large deviation above the coherence peak, which is again unusual.
Yeah, this deviation is observed at a bias higher than the coherence peaks, where we have the coherence peak. However, this deviation, we observed a slight zero bias peak at certain temperatures, which means higher than the lowest temperature. At elevated temperatures, this was observed, and this might be due to because some unconventional parameter order.
No, this happens all the time when you have a superconductor tunneling. Your tip has picked up a bit of superconductor. So this fit with a single superconductor normal formula may not be reliable. Okay, we can continue this discussion.
I suggest maybe you continue the discussion later. Okay, let's thank Aastha for interesting talk. Let's move to the last speaker of the session. Can the last speaker connect their slides, computer? So the last speaker is Soumyajit Mandal. He's going to talk about phase fluctuations in a-MoGe thin films fermionic to bosonic transition. So over to you. At 10-minute mark, I will remind you, Soumyajit, that you have about 3 minutes to finish up so that we can have questions.
Yeah, thank you. You can see the slides?
Yes, please proceed.
Oh, okay, thank you. Hi, I am Soumyajit. I am from Professor Chatterjee's lab in TIFR Mumbai. So I will be talking about the effect of phase fluctuations on amorphous molybdenum germanium thin films fermionic to bosonic transition. So this will be the contents. The brief discussion about these two mechanisms and the measurements. We have done the measurements on transport, scanning timing spectroscopy, and two-coil measurements. And then with the results, we will show the transition from the fermionic to bosonic behavior. So let us start with this question. So let us first start with let us first see how the disorder affects the superconducting transition temperature, or TC. It can have two origins. So in case of
in case of harmonic root, what happens is that the TC is suppressed in presence of disorder scattering, because repulsive Coulomb interaction dominates over the attractive pair interaction. And here the superconductivity parameters more or less follow the conventional Bardeen-Cooper-Shepard behavior. And on the other hand, for the bosonic case, the superfluid density itself gets suppressed due to disorder, and the superconductor becomes more susceptible to phase fluctuations. So eventually, at a critical disorder, the superconductivity gets destroyed because of the loss of phase coherence, and then we can see superconductivity gap even above the transition temperature. So we call it pseudo gap, and we can detect the pseudo gap in our scanning tunneling spectroscopy measurements. So now the question is, are these two roots, the fermionic and bosonic roots, are they exclusive, or can a superconductor follow the mechanisms, both mechanisms at different levels of disorder? We'll see in our measurements. So this is our system, amorphous molybdenum germanium thin films. So it was grown by pulse laser deposition technique, and the disorder was here the disorder was tuned by changing the thickness. And one important motivation for choosing this material was that the earlier measurements on this a-MoGe was that it followed the harmonic route in these measurements, and but most of the results were transport results. So we'll see we'll see in our measurements for all the three measurements. Let us just start with the transport transport measurement. So here what happens that we have plotted the transition temperature with the normal state surface resistance, and the data we have plotted with the finger strength fitting, which is based on the harmonic mechanism, where the suppression of TC was due to the due to the increased Coulomb interaction. So as you can see, the fit matches very good at least at the low disorder. So we'll see in the other measurements how this behaves in the materials. How can you get? So we are going to the scanning tunneling spectroscopy. So at first I will give one line introduction to how this tunneling happens. So here what happens is that we place a very sharp tip and it places two very close to the surface, so that we get the contact tunneling happens between the tip and the surface. And here the important parameter is that tunneling differential conductance, which is proportional to the superconducting density of states. So here you can see that so here you can see at the lowest temperature, you can see the gap here. And as the temperature increases, the gap fills up. And we have just converted these type of graphs to a intensity plot of intensity plot of this this conductance spectra, where the x-axis is the temperature. Here you can see the blue line is the gap you are seeing in that, and this is the 11 nanometer sample, and here along with the spectra we have also plotted the RSDR. So as you can see that that the gap vanishes at almost the same temperature where the resistance occurs in the RS. In the RS has a temperature plot. So it is expected for the conventional superconductor or the low disorder sample, but as we go to the as we go to the low thickness, we can see that the gap starts to exist above the transition temperature. And you go to if you go to the 2 nanometer sample, we can see that the gap exists even above the double of the transition temperature as we got in the resistance. So you can see that this pseudocap this pseudocap starts to appear at the as we go to the lowest temperature. And now we are going to the Tuchel measurements. So this Tuchel in this Tuchel measurement, what you do is that we place the sample in between two coils, and we pass a small AC current through the primary, and we pick up the voltage in the secondary, and the superconducting response of the superconducting sample is captured in the mutual inductance. Inductance like this. So from that we can extract the penetration depth by calculating the Maxwell equation and the London equation for the whole setup, because we have the parameters of the coil parameters. So by the parameters we can extract the values. So that's the measurement part. So we can see how so what result we have got. So here at the 1 by lambda square of the temperature variation of the 1 by lambda square for different thicknesses. So the black curve is the highest thickness, the 20 nanometer, and all the other curves in the decreasing order. So here you can see that the 1 by lambda square falls by around 1 order if we go from 20 nanometer to 2 nanometer. If you go from 20 nanometer to 2 nanometer, and also we could fit the curves in the higher and higher thickness for the 12 nanometer and the 20 nanometer by the dirty VCS fit by this formula, and also we compared the zero temperature means the zero temperature values of different thicknesses with the zero temperature BCS estimated value, and the means as you can from this curve that this as we go to the lower thickness, it goes to the it falls below the 5 nanometer thickness, and also you can see from there that for the 2 nanometer sample it goes around like
Soumyajit, you have 3 minutes to finish up.
Okay, yeah. So then the suppression is like 50%. The suppression for the 2 nanometer sample is like around 50%. So we have estimated the suppression from the experiment by the quantum fluctuation approximation. The calculation, it is coming like 0.78. So the mismatch in the theoretical and the experimental value might be because that the inhomogeneity in the lowest thickness sample was not included in the calculation, and although the value is in the same range, and the classical and the temperature variation, the 1 by lambda square also followed a linear behavior, which is which follows the classical phase fluctuation calculation. So now to conclude, I will just compare two energy scales from two measurements. Like one is the JS, which is the superficie stiffness from the penetration depth measurements, and another is the superconducting gap from the scantinely spectroscopy. So as you can see, at the higher thickness samples, the JS is much greater than the delta, which is also the case for the conventional superconductor. We see that means that the JS is the phase is digit in the superconducting state. But as we go to the lower thickness sample, the JS becomes compatible to the superconductivity gap. So it means that it becomes more and more susceptible to phase fluctuation. So this picture portrays very beautifully the transition from the harmonic regime to the bosonic regime. So to do the summary, that we have seen the harmonic signature at the low digital, that is at the higher thickness sample, and the bosonic behavior at the lowest thickness, lowest thickness sample, and also in this curve we could see the transition in the two energy scales. Thank you.
All right, thank you, Soumyajit. The talk is open for questions. I had a question, Soumyajit. If will the analysis, if there is some, so I'm not really familiar with sort of this area so much, but if let's say if there is some roughness in the film,
yes,
will that so affect the analysis? Let's say it's not flat 2 nanometers.
Yes.
But it's has a roughness of, let's say, 1 nanometer, which is not unusual. Then will the analysis have some changes?
Yeah. In the analysis means the theoretical calculation we have not included the in the inhomogeneity, but the analysis you mean the.
I see. Okay. All right. Satyabhat, maybe you can ask a quick question and we'll stop then after that.
Yes.
Yeah, please go ahead.
Yes.
So could you explain how did you get your penetration depth and superficial density from your two coil measurement?
Good.
Yeah.
I just keep that part. Means the I just okay. So at first we choose a set of lambda values, and we calculate from the coil parameters the theoretical values of the theoretical M values, and from that set we just pick the lambda values from our experimental values. Means we we have a table of M and lambda values, and from the experimental value we just pick the lambda values from the from the experimental M values. Am I clear?
Okay, thank you.
Okay. Are there any more questions? Okay. If not, let's thank Soumyajit and all the speakers in the session. The session comes to a close now. Thank you very much for giving your talks.
Hi. Thank you, Mandal. We have kept to the time. Thanks to both Mandal and the speakers for that. So we'll have a short break for getting a tea or whatever. And then the poster session follows. So I request everyone kindly go to the posters. There are about 70 posters. And we have made, it's an experiment where we have used frames that uses virtual reality. So we have tried to make it an experience as close to the physical poster sessions that one can have. So please visit them and enjoy, and see you for this